Okay, let's dive right into this explainer with an absolutely incredible story. We're talking about a January 2014 fireball that set off a massive scientific debate regarding interstellar visitors. We're going to unpack a wild journey that starts with a high-speed atmospheric detection by military satellites and takes us literally all the way down to the bottom of the Pacific Ocean. It's this fascinating mix of astrophysics, marine geochemistry, and a fierce modern-day scientific showdown over what exactly is sitting right now on the seafloor. So let's start with the boldest claim out there. There's a Harvard astrophysicist whose expedition might have recovered fragments of an actual interstellar object, or, if you really want to push the envelope, extraterrestrial technology from the ocean floor. Researchers Avi Loeb and Stein Jacobson did not hold back. They concluded they had uncovered something highly differentiated, extremely evolved, and of an entirely unknown origin. This was after a $1.5 million expedition on a massive catamaran called the MV Silver Star, where a Harvard-led team analyzed these microscopic droplets dredged from the ocean. They basically said, hey, these samples are completely unique, and they might just be from outside our solar system. To understand how this whole mystery unfolded over a decade, we need to look at the timeline. It all kicks off in January 2014. U.S. Space Command sensors detect a meteor fireball, officially known as CNEOS 2014-0108, or IM-1 for short. Now, because it was traveling at this unusually high velocity, well over 45 kilometers per second, it was flagged as having a hyperbolic interstellar trajectory. Basically, it was moving too fast to be from around here. Fast forward to June 2023, and the Galileo Project launches a major marine expedition off the coast of Papua New Guinea to actually go find it. But you know how science works, right? Shortly after they announce these groundbreaking discoveries, the broader scientific community steps in. By November 2023, you get alternative theories popping up, like industrial coal ash. And by March 2024, a huge rebuttal regarding the seismic data completely shakes things up. Dredging the Pacific seafloor. So the obvious immediate question here is, how on earth do scientists go about finding microscopic fragments of a single meteor nearly 10 years after it splashed into the ocean? Well, they pulled off a monumental feat of engineering. The team dragged this 200-kilogram sled packed with 300 neodymium magnets across 0.06 square kilometers of the seafloor, under 2 kilometers of water. And they used this really fascinating four-step process to sift through all the muck. First, a wet magnetic separation washed away all the biological matter, like deep-sea plankton. Then, the magnetic fraction was dried out and passed through physical sieves. Next up, a secondary dry magnetic sweep isolated the metallic spherules from random volcanic sediment. And finally, researchers manually extracted particles larger than 100 microns using non-magnetic tweezers under digital binocular microscopes. I mean, think about that, finding about 850 microscopic specks in the pitch-black depths of the vast Pacific Ocean. It's just incredible. The result of all that sifting was a massive concentration of these spherules, aligning perfectly along the expected path of that 2014 meteor. Now, the team did actually try to do some initial elemental screening right there on the ship using an X-ray spectrometer, but the microspherules were just way too small. They really needed the state-of-the-art geochemistry lab back at Harvard to figure out what they had truly found in those high-density zones. The BeLaU discovery. The plot thickens when the Harvard lab gets their hands on these tiny spheres. Out of the 850 fragments, most of them were just normal cosmic spherules, but a tiny fraction of them were incredibly different. They found 5 highly unique spherules that they dubbed BeLaU, which displayed a chemical composition completely unlike any known solar system material or natural meteorite. BeLaU stands for Beryllium, Lanthanum, and Uranium. Not only were those elements highly enriched, but volatile elements like zinc and lead were heavily depleted. And that depletion is exactly what you'd expect to see from evaporative loss when a meteor undergoes a fiery airburst through our atmosphere. They even found mass-dependent variations in iron isotopes that backed up this whole rapid heating and cooling theory. To put this into perspective, these specific spherules showed an excess of beryllium, lanthanum, and uranium by up to a factor of 1,000 relative to our solar system's standard chondritic meteorites. 1,000 times! The research team pointed out that an abundance pattern this extreme just doesn't match the Earth, the Moon, or Mars. They suggested this unique chemical signature could only originate from a distant, highly differentiated planetary magma ocean, or, as you might have seen heavily hinted at in the media, maybe something even more exotic, like alien technology. So, just as the evidence for this interstellar discovery started looking incredibly compelling, we get a massive plot twist. You've heard the saying, extraordinary claims require extraordinary evidence. And pretty soon, several independent researchers began picking apart not just the chemical analysis, but the foundational data used to find the spherules in the first place.
The coal ash counter-argument. Let's look at the scientific pushback, starting with a surprisingly mundane explanation for those exotic chemicals.
University of Chicago researcher Patricio Gallardo published a completely different analysis. He compared the BeLaU signature to terrestrial materials and showed that this unique chemical makeup actually strongly matches the industrial waste left behind by coal combustion in power plants and steam engines. So rather than a highly differentiated exoplanet, this counterargument is basically saying, hey, these spheres are just a specific type of human-made industrial pollution that's been collecting on the seafloor for decades. Now, Avi Loeb pushed back hard on this, arguing that the coal ash claims superficially examined only a few elements out of the dozens they analyzed. But for sure, the seed of doubt was planted. Adding to the skepticism, astrophysics professors Stephen Desch and Alan Jackson calculated the physical realities of the meteor's atmospheric entry. They noted that if this thing was truly interstellar and slamming into the atmosphere at over 45 kilometers per second, the friction would be so absolutely intense that 99.8 to 99.99999% of the object would have just vaporized. According to their mathematical models, practically nothing of significance would have survived to reach the ocean floor, which makes the retrieval of actual meteor fragments highly, highly improbable. A signal from a truck. But the most dramatic rebuttal of all came from a re-examination of the seismic data itself. Remember, the ocean is massive. To narrow down their search grid, the original expedition relied on vibrations recorded at a seismic station on Manus Island, while Johns Hopkins planetary seismologist Benjamin Fernando and his team took another look at that data. And they concluded that those ground vibrations weren't from a meteor at all. When they analyzed the signal, they realized it actually changed directions over time, perfectly matching the characteristics of a heavy truck driving past the seismometer on a nearby road. That's right. Instead of an interstellar visitor, they may have just been tracking a passing semi-truck. Fernando's team flat out stated the signal had all the characteristics of a truck and zero characteristics of a meteor. Fernando's team then went a step further. By comparing the heavily searched area with broader acoustic data originally built to measure nuclear tests in Australia and BeLaU, they determined the actual 2014 fireball was likely over 100 miles away from where that truck signal was recorded. The takeaway? The expedition used the wrong signal and was dragging their magnets in completely the wrong place. Naturally, the Harvard team countered this. They pointed out that the nuclear test acoustic data has a huge margin of error and reminded everyone that they relied much more heavily on the original Defense Department satellite coordinates anyway. Science in action. So what does this all mean for us? The real takeaway here isn't just about who wins the argument. It's about watching this fierce dialectic play out in real time. Despite all the intense skepticism regarding the spherules and the truck signal, a recent statistical analysis of the government sensor data offers a really compelling counterpoint. Even when you account for potential measurement errors in the military satellites, the analysis calculates a 94.1% probability that the original 2014 meteor was indeed on an interstellar, unbound orbit. Now, yes, 94.1% is slightly lower than the 99.7% confidence usually required for a formal scientific discovery, but it absolutely remains the most mathematically probable explanation for the raw data. The interstellar meteor likely happened, even if finding its leftovers is a massive debate. At the end of the day, whether those recovered spherules are alien technology, natural interstellar rock, or just passing trucks and coal ash, this investigation was a real game changer. It successfully pioneered a brand new way to do astronomy. The expedition integrated military satellite tracking, atmospheric ablation modeling, and deep-sea marine geochemistry all into one mission. They proved you can actually tow a magnetic sled across a targeted zone of the ocean floor and recover microscopic particles. They essentially created a physical framework for future interstellar astronomy, literally turning the Earth itself into a giant fishing net to catch passing cosmic material. As you process all this, I'll leave you with a final thought to chew on. The hunt for interstellar material right here on Earth has officially begun. The Galileo Project is already planning their next expedition to gather more samples and get more controlled data. So, will our first universally accepted, confirmed, physical piece of another star system be dredged up from the ocean floor? Or is it still out there in the deep blue, just waiting to be found?